I'm Sam Hadden. I'm a graduate student here at Northwestern in the Department of Physics and Astronomy. I think we've all had the experience of looking up at the night sky and wondering what else could be out there. Are there other planets like in our solar system? And what are those worlds like? Are they places that could be habitable? Maybe you guys heard the exciting news recently that a planet orbiting our nearest star, Proxima Centauri, has just had a planet confirmed orbiting it that could potentially be habitable. And so today I'm going to tell you a little bit about the progress we've made in the past few years in answering the question of what are other worlds like and what is out there, and I'm going to tell you a little bit about my part in that as well. So what's really been revolutionary over the past few years for understanding planets around other stars or exoplanets has been the Kepler telescope, or NASA's Kepler mission. This was a space telescope that was launched in 2009. It was designed specifically to be able to detect an Earth-sized planet orbiting another star in our galaxy that could potentially be habitable. And to date, it's responsible for most of the exoplanets, the bulk of the exoplanets that we're aware of in our galaxy. What you're looking at here is a snapshot of all of Kepler's discovered exoplanets. Each one is represented by a white dot here. So this is quite astounding. There's thousands of them. And I've arranged them by their orbital period, or how long it takes them to go around their star, and their size on the vertical axis. And I've shown the solar system planets for reference. And so you can see there's a wide range of orbital periods and sizes. So how does Kepler find these planets, or how did it find these planets? It uses what's called the transit method, or the transit technique. And the basic idea is Kepler went up in space and stared at a bunch of stars. And what it did was monitor the brightness of those stars. And anytime a planet happened to pass between us and the star, when it did so, it would block a little bit of the brightness that we observed coming from that star and would make a little dip in the brightness, like shown here. And Kepler would discover planets like this and would wait and watch them come back around. And this is how it characterized planets. And so the two things that this tells you about planets is they're the things that I showed earlier, basically. Just their orbital period. That's how often it comes back around and causes a dip, and how big they are. And that's just related to how big of a dip it causes in the light that we see from the star. A bigger planet makes a bigger dip. And so one of the big surprises that came out of this mission was that there's all these planets that are in between the size of Earth and the size of Neptune, which is our solar system's next largest planet. And so we have no baseline for what to expect these planets are like. This was really surprising. And if we want to know more about these planets, what's crucial is we need to know how massive they are. That tells us for a given size planet, if it's really massive, then it's probably a scaled-up rocky version of Earth. Or if it's lower in mass, at the same size, then it's probably fluffy and covered in gas, like the outer solar system planets. And so I'm going to describe a technique that I use to measure masses of planets. And the basic idea is this. If you have a single planet going around a star with nothing else in the system, then you can basically set your watch by when you expect that planet to pass in front of the star. Each little one of those dips will come right on time, and you can line them up by when you expect them to arrive, like in the cartoon on the top here, and they'll fall right where you expect them. If you have other planets going around the same star, however, the planets will feel gravity not just from the host star that makes them orbit, but they'll also exert gravitational tugs on one another as well. And the consequence of this is that each time the planet comes around, it'll come a little bit early or a little bit late relative to when it would arrive if it were just there by itself. So it'll sort of dance back and forth around this line of expected arrival time. And so we can use this effect to measure the masses of planets. Basically, the size of the effect is a proxy for how massive the planet is that are yanking on each other. So if you have a more massive planet, it causes larger variations, and you can infer, say, that you have a rocky, scaled-up version of Earth that's causing variations in the transit time. Whereas if you have smaller variations, you can say you have a smaller mass planet. So you can convert these sizes of these variations to a mass of a planet. And so here I'm showing a lineup of planets that I've been able to successfully apply this technique to in order to infer a mass for these planets. And what I've done is I've broken them down into, using their mass and size, I've broken them down into a composition based on how much rock and how much gas they have. And so I'm showing a rock core in brown on the inferred amount of gas on top in an envelope in blue. And so you can see, just from a quick glance, that a lot of these planets are covered in a fair amount of gas. And typical numbers for these planets is that 90% of their mass is accounted for by a rocky core, roughly, and about 10% of their mass is accounted for by gas on top of them. For reference, the amount of gas on Earth is pretty much negligible, and for Neptune, it's about 5 or 10% of Neptune's weight. We actually don't know much better than that. And so this is a really exciting step forward into understanding what other worlds are like. This tells us, first, that they must have formed early during the lifetime of their host star while gas was still around. So gas sticks around a newborn star for about 10 million years. And so these planets must have formed pretty quickly in the lifetime of their stars to have been able to get some gas while they were forming. By contrast, in our solar system, the inner terrestrial planets, like Earth, formed after about 100 megayears or 100 million years, so about 10 times after all the gas would have gone away. And so this raises a question, if these planets are so common, why didn't we form these Kepler-type planets in our own solar system? And what sets the conditions that allows these types of planets to form? So there's a lot of open questions to understanding how planets are like in general and where our solar system fits in that context, and there's a lot of work to be done. Thank you.